Whitaker sends his regards. He won a big contract. He's deep in leading his team to successful submission of their required documentation, so he sends his deep regrets. I'll say a few words about that later when we have some time at the end of this session. Now I would like to present Mitch Weiss, who was the project engineer for the Space Shuttle Robot Arm. He is the Chief Operating Officer of Seabird Corporation in Pittsburgh. That is a Carnegie Mellon spin-out. They make the world's most sophisticated, in fact, indeed, only autonomous mobile visually guided robots in industrial use. Mitch, thanks very much for coming.
I got it correctly. I was a summer intern on the show. Okay, I push buttons and stand here to remind you to do all these things at once. I'm good. I got my own laser. There's been a lot of talk today about space habitats and people and membranes for getting us up there and doing all that good stuff. Okay, why is that? We heard a lot about that, and we even heard somebody say that 100% of the people mining will be people. I'll just agree with that before I even start. We'll replace all those people with robots as fast as we can. I want to give you a little bit, this presentation I put together is full of pictures and videos and very few word slides. Hopefully I'll keep you awake because going after lunch is always a bad thing. It's sort of stuff that might do things like that. Talk about how it works, and then some of the challenges, and how we'll use it. For starters, the thing we make is something we call an industrial mobile robot. So some of you, actually it's just a really deep robot crowd, but then again, I don't know what makes mechanics. You might be familiar with guided vehicles, you might be familiar with the Darwin Grand Challenge that they did, which was essentially mobile robotics. The thing that we think differentiates it from guided vehicle technology, teleops, and everything else is the robot itself is completely autonomous. It's not tied to a base station, it's not dependent on infrastructure changes. Everything it needs is on board the robot. The other thing that we do is try to make sure that we can follow Moore's Law on the curve. And here in the Valley, hopefully everybody knows how wonderful Moore's Law is. My previous 15 years of business was in the semiconductor industry, making sure we can keep going. Of course, every 5 years we say we're going to hit the wall, Moore's Law can now continue for another 5 years. It's kind of like fusion. You know, it'll happen. All right, the history of it. This is Hans Moravec. He's one of the founders of Seagrid. And back in the 70s, while he was at Stanford AI working on his PhD thesis, he developed this gizmo called the Stanford Cart. The Stanford Cart, for all you robot wonks, is the first stereo-guided robot ever made, period. And he used to prowl the hallways at Stanford AI. Prowl is a strong term. See, building something like this was so expensive in the 70s that it had one camera on it. So to do stereo, the camera moved on little legs. And then the robot moved a little bit forward, the camera moved aside, took its two pictures, and the robot moved and carried its large bundle of cables that went back to the backs that was driving it. All that good stuff. This is actually a later robot one. He had a CMU, which is currently in the engineering space with Seagrid. So another little bit of the history. This is the room that the Stanford Cart first navigated. And all these little spots indicate features it was able to find. in this very rich room, those are the features it actually identified. And getting across this room took a day. And part of what we're looking at here is the advancement in what computing does for you. So in the 80s, late 70s, when we got this thing going, we had about 1 MIPS available for $1,000. It seems to be, for any researcher, the available amount of computing they can buy, because their department head would give them $1,000 towards computing. In the 90s, this is a hallway, and I was at a conference a couple of weeks ago where they called these the banana shapes, which shows you the inaccuracies of mapping. But this is a hallway that was mapped using ultrasonic sensors, sonar. Everybody who works in the world knows what sonar sensors we use. The ones off the Polaroid SN70 cameras. Right? You can still buy those. There's actually companies that now makes those things. So we have about 30 MIPS, and we're able to generate 2D maps. And to make that work, Hans developed a technology called 2D evidence rooms, where you take each subsequent picture from a different perspective, and you add what you learn from each picture into an a priori built grid of information. So what this does for you is get rid of noise problems and uncertainty problems. If something's there for 1 out of 5 pictures, the probability that it's real is pretty low. If something's there for 5 out of 5 of your snapshots, the probability is pretty high. So it's stuff into the grid. You keep adding these probabilities into grid cells, and you eventually build a pretty accurate map of this hallway and CFU with all the doorways. That was about 30 MIPS processing power to do that in sort of real time. Every one of the Grand Challenge vehicles uses some form of 2D evidence grid technology for part of its mapping and method. They, of course, all use GPS, so most of the time they're on GPS. This is about 2000, and Stuart started in 2002, which is when Hans left. CMU. And this was his office, so I don't really believe that, because I've seen his office in secret, and I know that his office is. And this is what's done using stereo cameras, building a 3-dimensional map. This is not a photo of this, but in fact a whole potload of data points onto which he projected the color that was taken by each picture and where the colored body should be, to see if the model was building a reasonably realistic model. So that's sort of just a tool. And we're running about 1,000 minutes. This is our wonderful conceptualized vision of a thing we call an EML, an extended local map. So you build maps in little chunks that are cubic, and you can chain maps together. And that turns out to just be a reasonable way to do the computing. You don't want to build a whole map of the world into your system at once, when you can only look at stuff you can see. I added it, don't get too close. I added this slide this morning while I was sitting here, because I thought it would be useful. We've all seen the Moore's Law curve. Every 18 months we double processing, or every 18 months you cut the cost in half, or every 18 months the size of the transistor gets cut in half, or whatever your interpretation of the law is. This is something that didn't have a name, so we call it market extrapolation. And Hans has been for years. He's written a bunch of books on this stuff, tracking the computing power of all these different computers and processors that hit the market, trying to draw the extrapolation curve and comparing it to some critter in the bio world, our world. So about 2000, the belief was we were about the place where you get the smarts of a copy for $1,000 worth of compute. So our product, this thing, there's a picture up there, we call it the GPA, which means General Purpose Eight-Ton Transport System. But GP is really copy, it's our giant inside joke. None of our customers will ever know. got to figure out what we do for our wizard actor. Anyhow, we're already pretty well past the government stage right now. This curve is outrageously predictive. We've been on it. Hans has been updating it for 15 odd years, and if anything, it's accelerating. So I want to talk about how we apply all that stuff. This is a pallet truck. You've probably all seen pallet trucks out there. Pallet trucks are an incredible commodity product. Buy them for $10,000. There's 20 odd companies in the world that make it. $10,000 is about what the steel is worth. And it's a cutthroat business. My understanding is the dealers who sell it make about $200 a truck. We had a bunch of stereo cameras right here on the top of the truck. Spent a whole lot of money on safety-rated things that won't run into people. And then you can sell a truck for about $70,000 to $100,000. Trust me, it doesn't cost me $70 grand to add the cameras. That's because, and I didn't see this in any of the presentations, the most expensive thing about a truck is the guy driving the truck. It costs about $3 an hour to operate a truck. It costs about $25 an hour to put somebody on it to tell it where to go. So if we start to look at all these costs involved with getting into space, and all the costs that wrap around the people in space, you start to say, wow, robots, the reason we do all this expensive stuff on Earth is to get rid of $25 an hour guys. Although in Europe, they're $40 an hour. This seems like a wonderful market. So this is a little video, a little short one of these things running around in a warehouse. This type of robot is a little different from where most robots are used. Most robots are used in factories. Factories are very stable, controlled environments. Warehouses are a little bit nutty. This actually is a factory right now. The reason robots aren't used in warehouses is because of the tasks that happen in warehouses. Sometimes you want to get all the Hershey candy bars to move out to the store, and sometimes you got to move the Cheerios. Sometimes it's the soup. So the guys who are driving these trucks around, you can see some pictures of that, they're doing a different task every single time. So a guided robot that's tied to the infrastructure of the building isn't flexible enough to do the job. So here we have this technology that we're shipping out to the field that using just vision, as these stereo camera pairs we mount to it, can go anywhere we want it to in the warehouse. Without a guy pushing a joystick, right? So some of the spaces we're in, this is, I'm sure you outer space types don't spend a lot of time in distribution centers. This is a grocery distribution center. You go buy your Cheerios, they're coming out of a place that looks like this. These things are typically 250,000 to 500,000 square feet, 40 to 60 foot high ceilings, a couple of hundred people running around on lift trucks. This to me looks like out of a hell. And in fact, the vision challenges here are a lot of stuff close to the side with a lot of changing features, so they're not useful. But up towards the top and down on the floor, there's a lot of useful features. So you have a nice wide field of view up and down. This is the loading dock area of such a warehouse. And the challenges here is here the guys on the trucks creating traffic in front of the nice autonomous one that's trundling around. And the other thing that's important about it from a features perspective is you can see there's a lot of wide open space, and then there's a lot of those tunnels to enter in. So technology has to do that. So in my vision of man colonizing the moon, this is the base operations center. We're sending out, bringing all the things back that we're mining. This is a picture of a toilet factory, because being in the robotics business, you are always doing glamorous work. This is what's called a bulk warehouse. You see no racking, they just store stuff on the floor. These spaces, think about these things, 250,000 square feet. You're out looking at the horizon, featureless floors, stuff there one day, nothing there the next day. And then the very narrow aisles, again looking like canyons or valleys. All right. This is how we use the stuff. This is how we do it in factories. A person walks the truck through the facility, takes pictures of the environment, turns them into stereo point clouds, populates the evidence grid with the stereo point data. Then, as an offline process, we build the models. So this is a 3D hallway. This is what it all looks like constructed. You see these spaces off through the doorways. It shows you that as the vehicle's driving by the doorways, it is gaining information about what's behind the walls, which you can't see from one place. So one of the things that we really take advantage of is traversing the terrain, if you will, to learn about. And then in the factory, what we do, or the warehouse, is we do this walkthrough, we build a model, and then we let it run. This video is what the cameras, we use 4 or 5 pairs of stereo cameras, so we have 360 view. This is what one camera is seeing while a guy is walking a truck through the warehouse. And all the green dots, which you can't see too well on that screen, are the features it's grabbing in each glimpse. So we do this at about 5 glimpses a second. And if you see the really bright screen I have in front of me, you see that we get a few thousand features on each glimpse. So if you think about trundling through kilometers of pathway, and we can run about, I think we can store 25 miles of path on a 160 gig drive. If you think about how many millions of points we're finding in the environment, you answer the question you should all inevitably have of, well, what happens if the environment changes a little bit? You know what? I got thousands of features. If half of them match, and I think I'm about where I am, pretty good chance I know where I am. So that's what makes this a rich, robust, not too fragile system. Now something you can see through the video is these going in light spaces, dark spaces. Of course, the cameras adjust for the light and dark. The features don't really change in light and dark unless the shadows are moving. It all comes down to how you mess with the cameras and compression, dynamic range, and all that good stuff. So we did a little work last year for our friends at the Tank and Automobile Research and Development something or other at the Army. And they want to know if this stuff could work outside. So there's one of the vehicles trundling along outside our old building in Pittsburgh, Lawrenceville. And I'll cut this one off early, but what I want you to see is it's going to go from very bright sunlight through shadows, around the corner into a dark shadow. We ran the system on rainy days, on sunny days, on cloudy days. Next page you'll see some snowy days. We can't run fast enough, obviously, we've got vehicles yet. Not obviously, we can't process fast enough to guide a vehicle doing 30 miles an hour. We should be there in about 18 months. So they're just going to go around the corner. And you see how wide open the space is. So things like the chain link fence and the shadows, all that good stuff. This is how we showed it to the Army. This is a truck with a camera on it, a couple of GPS units, and we would turn the GPS units on and off so people could see the thing was still navigating. And we drove it around Pittsburgh. That's snowy. And these are the pictures of the cameras. We're just kicking off the project. This is where it should get interesting for you guys. Well, I got to use some words before I run out of time. The thing the Army called what we were doing was GPS denied navigation. When the convoys are running through the streets of Iraq these days, they have to jam all the radio signals so their GPS units don't work. It started out with the bad guys who were jamming the GPS and created a problem. Now the good guys have to jam it to stop the cell phones who don't want to be IEDs. So GPS denied navigation is a big concept of that. Well, of course, inside a warehouse, we're always in GPS denied environments. The next thing that we want to work on for the good of the country and everyone else, is this concept of taking 3D models built from satellite data, or they could be built from UAVs. And given that we get a bunch of pictures with georeference data for those pictures, or imagine a bunch of pictures of the surface of an asteroid or the poles of the moon. I saw excellent data on the screens today. We're going to do the work next year to run those pictures through a system that builds a model that you can then direct the rollout. So the idea of being able to mine on the planet, go anywhere we want, is going to be as simple as a zero infrastructure, take a lot of pictures of the surface. On the screen, probably we'll develop a little touch screen interface to draw the route you want it to follow, send that command up, and then there's no real-time control of the road required. So whether you're on Mars or on the moon, or yuckity yuck, we don't care. There's no localization infrastructure, no GPS, no beacons, and oh, by the way, the automated rendezvous and docking stuff, perfectly applicable to this kind of technology, vision technologies. It's a hostile environment, so you can't send people out there mapping the place with lasers and other photogrammetry tools. So we'll just take the satellite pictures and the radar pictures and all the other stuff. And it's a changing environment, so you need something to throw up. Last slide. So the way we're going to fix that is with this offline mapping technique. We take the photo data, build the maps, mission planning system that allows you to do what are the goals, definitions separately from the mapping and localization. And that lets you run autonomously. Of course, the next thing that our robots need intelligence for is exception handling. And you can run a whole bunch of places, including underground environments, where you have to provide some lighting. And we are working